Right now, somewhere on the internet, two developers are arguing about whether to rewrite a service in Rust or Go. One side says, memory safety, zero-cost abstractions, ownership model. The other side says, simplicity, fast compilation, readable concurrency. Both sides are completely convinced they are having a new argument. This exact argument, control versus simplicity, explicit memory management versus garbage collection, expressive type systems versus minimal syntax, was already crystallized before 1965. The languages that first made these trade-offs explicit are what we call prototype languages, or archetypes. And here is the uncomfortable truth that should keep you watching. Every heated debate you have ever had about language choice was already decided, in principle, by designers who were working with punch cards. By the end of this lecture, you will be able to name exactly which 1958-era design your team is currently losing. Let us be precise about the cost, because this is not an academic question. Team selects a language without understanding its ancestral design assumptions. They do not simply choose a tool, they inherit a worldview. And if that worldview conflicts with the problem domain, the team will fight the language's grain for the entire lifetime of the project. Consider a concrete pattern. A startup builds a high-throughput data pipeline in Python because the team knows Python. 2 years later, they are wrestling with the GL, the global interpreter, spending engineering cycles on workarounds that Go or Rust would have made structurally impossible to need. The root cause is not Python. The root cause is that Python descends from a prototype that prioritized human readability and scripting flexibility over concurrent execution. Choosing it for a throughput critical system is a design mismatch, not a skill failure. The ancestral assumption was wrong for the domain. This distinction, design mismatch versus skill gap, is exactly what senior engineers and information technology strategists must be able to diagnose. And diagnosing it requires knowing where the language came from. That diagnosis framework is what this entire lecture builds. Before we go further, let us be explicit about what this lecture will actually give you: 3 concrete, transferable skills. First, you will be able to trace any programming language, past or present, back to one of 7 prototype archetypes, not approximately, precisely. Second, from that ancestry alone, you will be able to predict the language's type system philosophy, its memory management model, and the concurrency primitives it will naturally support or structurally resist. Third, and this is the skill that matters most in architecture reviews and technical strategy discussions, you will be able to explain paradigm collisions. When a language hybridizes 2 archetypes, such as Scala, merging lineage, object orientation, with ML lineage type inference, you will know exactly where the friction points will emerge and why the community will argue about them forever. These are not soft observations. They are structural predictions derived from design genealogy. The information technology strategist who can make these predictions in an architecture meeting changes the quality of the decision being made. Let us now look at the map that makes all of this possible. So here is the complete map, the entire universe of programming language ancestry, reduced to 7 nodes. At the center of everything, 7 prototype languages, each representing a fundamentally different to the question of what a programming language is for. Lisp, born 1958, answers. A language is a notation for symbolic reasoning and computation itself. Fortran, 1957, answers. A language is a tool for expressing mathematical formulas efficiently for a machine. COBOL, 1959, answers. A language is a medium for business process description, readable by non-specialists. APL, 1962, answers. A language is a compact mathematical notation for operating on arrays as first-class entities. ALGOL, 1958, answers. A language is a structured, block-scope description of algorithmic procedure. Simula, 1967, answers. A language is a simulation of real-world entities and their interactions, giving us objects. And ML 1973 answers. A language is a formal system with a type algebra that can be proven correct before execution. 7 answers. 7 worldviews. Every language you have ever written in is a descendant of one, or a hybrid of 2, of these 7. In the next chapter, we will confront the question that should already be forming in your mind. Why exactly 7? Why not 12 or 3? The answer is more rigorous than you expect. Here is the question that separates a language designer from a language user. What is the minimum set of decisions that, once made, determines everything else about a language's behavior? Not syntax, not standard library, not tooling. The answer is 3 invariant questions, and a prototype language is any language that introduces a fundamentally new answer to at least one of them. First, what is a value? Is it a number in a register, a symbol in a heap, a record in a file, or a mathematical function? Second, how is time modeled? Does computation proceed as a sequence of state mutations, or as a series of reductions with no mutable state at all? Third, who owns memory, and when is it reclaimed? The programmer, the runtime, the type system, or the hardware? Every design choice you have ever debated, garbage collection versus manual allocation, immutability versus mutability, objects versus functions, is a downstream consequence of one of these three questions. A language that gives a new answer to even one of them earns the status of prototype. Everything else is a derivative, and that distinction is not a matter of opinion. It is the structural criterion we will use for the rest of this lecture. But here is what surprises most senior developers. There have only ever been 7 distinct answers across all 3 axes combined. We will prove that claim, step by step, starting right now. Let us make this concrete. Take Java. When Java was introduced in 1995, the industry described it as revolutionary, and in terms of deployment model and ecosystem, it genuinely was. Write once, run anywhere, automatic garbage collection. Object-oriented by default, but ask the 3 invariant questions. And what do you find? Values in Java are objects or primitives, the same duality that Simula set to establish 30 years earlier. Time is modeled as sequential mutable state, the same answer Fortran gave in 1957. Memory is owned by the runtime garbage collector, a model Lisp pioneered in 1958. Java gave 0 new answers to the 3 invariant questions. Kotlin gives Java better syntax and null safety. Swift gives Objective-C better ergonomics and ARC. TypeScript gives JavaScript a static type layer. These are all meaningful improvements, do not misunderstand me. But they are ergonomic derivatives, not architectural prototypes. The critical distinction is this: a derivative changes the surface you touch, while a prototype changes the model you think in. Now, and this is the micro-test I want you to apply to every language you encounter, ask yourself, does this language force me to think differently about what a value is when things happen, or who controls memory? If the answer is no, you are looking at a derivative. If the answer is yes, you may have found an 8th prototype. No one has yet. Now let us formalize this into the classification grid that we will use for the entire lecture series. The 3 invariant questions form 3 axes, and when you map every historically significant language onto these axes, exactly 7 distinct cells are occupied. No more, no less. Look at the table. On the value axis, numeric scalar, symbolic expression, business record, array as value, typed algebraic structure, object, with identity, and event as value. On the time axis, each prototype chose either sequential imperative, recursive applicative, or concurrent reactive. On the memory axis, programmer manual, runtime GC, or type system enforced. The 7 cells that are actually occupied correspond to exactly the 7 languages we will study: Fortran, COBOL, APL, Simula, and ML. What is remarkable, and this is the insight that most language theory courses miss entirely, is that the remaining cells in this combinatorial space are either physically impossible to implement consistently, or they collapse into one of the 7 occupied cells under analysis. This is not an arbitrary list someone assembled for convenience. It is topological constraint of the design space itself. And that is precisely why, when Rust appeared in 2015 with a type system enforced ownership model, the entire industry took notice. It looked like it might be an 8th prototype. Whether it truly is, we will examine in Chapter 5. But first, let us travel back to the 1950s, because you cannot understand why only 7 answers existed without understanding the hardware and human pressures that forced those answers to be invented independently. To understand why exactly 7 prototypes exist, you have to stand inside the hardware reality of 1950 to 1965. This was not an era of abundance, where designers could afford philosophical experimentation. Every design decision was a survival decision. The IBM 704, the machine built for, had 32 kilobytes of magnetic core memory and a floating point unit that was considered miraculous. New scientists at Los Alamos and NASA needed to run ballistic trajectory calculations without hand-translating Fortran into assembly every day. That single pressure, batch numeric computation at the limit of hardware, is why Fortran's value model is a scalar number. It was not a design preference. It was the only answer that fit the machine. Meanwhile, MIT, Marvin Minsky, and John McCarthy were attacking a completely different problem: symbolic reasoning for artificial intelligence. Their machine had no floating point unit. Their data was not numbers, it was lists of symbols representing logical propositions. The hardware pressure was different. The problem domain was orthogonal, and therefore the answer to what is a value was necessarily different: a symbolic expression. At the same moment, the U.S. Department of Defense was watching corporations struggle with payroll and inventory. business regs spanning hundreds of fields, maintained by clerks who needed readable code, not mathematical notation. 3 different rooms, 3 different hardware constraints, 3 different problem domains, 3 different answers, and that is the key insight. The 7 prototypes were not chosen. They were forced into existence by the independent pressures of incompatible realities. The question we should be asking is not why 7, but how did they manage with only 7? Let us now place all 7 prototypes on a precise chronological axis, because the order of their invention is not arbitrary. Each one was a response to a specific unsolved problem that the previous prototype could not handle. Fortran 1957. The unsolved problem was numeric computation too slow to hand code in assembly. Solution: a compiler that treated the register as the primary value container. Lisp 1958. 1 year later. The unsolved problem was that Fortran could not represent symbolic logic at all. John McCarthy's answer was the S expression, a value that is either an atom or a list of values. And critically, Lisp invented garbage collection not as a convenience but as a mathematical necessity, because you cannot know at compile time how large a recursive symbolic structure will grow. COBOL 1959. Grace Hopper's team recognized that neither Fortran's numbers nor Lisp symbols could represent a payroll record with 47 named fields. The unsolved problem was human-readable business data. APL 1962. Kenneth Iverson, that Fortran handled scalars well, but arrays required explicit loops that obscured the mathematical structure. His answer was to make the array itself the atomic value, and suddenly matrix operations became single expressions. Algol 60 introduced block-structured scope and became the direct ancestor of every C family language. Simulus 67 added object identity and coroutines for simulation, and in doing so invented object-oriented programming as a side effect of modeling queuing systems. Finally, ML in 1973 answered a question no one had formally posed. Can the type system itself be a computational engine that proves program correctness at compile time? The Hindley-Milner type inference algorithm answered yes. 7 problems, 7 answers, each answer logically impossible to derive from any of the others. This is not a historical accident. This is topology of the design space, revealing its own boundary, and now we arrive at the illusion that every working developer carries, the convergence illusion. Look, modern Python, modern JavaScript, modern Java. They all have lambda functions now. They all have type hints or generics. They all have async await. On the surface, the languages look like they are converging into a single universal language. This feeling is so strong that a common argument in team architecture meetings goes, it doesn't matter which language we pick, they all do the same things now. That argument is structurally wrong, and I want to show you exactly why. When Python added lambda and map, it borrowed Lisp's syntax for anonymous functions. But Python's memory model did not change, so Python still uses reference counting with a global interpreter lock. Python's value model did not change. Values are still heap-allocated objects with reference semantics. The 3 invariant questions received 0 new answers. What happened was surface syntax migration, not computational model convergence. The underlying models have not changed since each prototype was defined. Fortran's register-centric value model is identical in spirit to what C uses today. Lisp's symbolic expression model is what Clojure Racket and Elixir's macro systems build on. ML's type inference is what Haskell, Rust, and F# implement. The prototypes did not evolve into each other. They each grew a larger and larger surface area of borrowed syntax, while their computational cores remained orthogonal. This is the most important intellectual frame I can give you for the rest of this lecture series. Syntax similarity is not semantic equivalence. And in Chapter 3, we are going to go inside each of the 7 prototypes and show you exactly what the computational DNA looks like, and why knowing it will permanently change how you evaluate any new language that lands on your desk. Let's begin with the oldest surviving archetype in products today, Fortran. When IBM engineer John Backus designed Fortran in 1957, he made one foundational bet: computation is numeric transformation. Not symbol manipulation, not word lookup, not message passing. Numeric transformation over arrays. This is a moral position, not a technical one. Performance is the primary virtue. State is explicit, local, and entirely under the programmer's control. The subroutine is the unit of abstraction, and it exists for one purpose: to transform numeric data efficiently. Now here is what most developers miss. When you write a NumPy vectorized operation in Python today, or when you define a Julia function that dispatches on array types, you are not writing Python or Julia philosophy. You are writing Fortran philosophy in modern syntax. The entire scientific computing stack, from BLAS and LAPACK through SciPy and MATLAB, is Fortran's design DNA expressed in newer notation. The key insight for language designers, and for the PE exam, is that Fortran separated the concern of what to compute from how to schedule memory access, which is exactly what modern GPU programming models like CUDA still do. But Fortran's array is a container, a box you put numbers into, and assumption, as you will see in the very next scene, is about to be demolished. Now contrast that with APL designed by Kenneth Iverson in 1962. This is where most CS curricula stop teaching, which is a serious mistake. APL makes a radically different claim. The array is not a container for scalars. The array is the atom of computation. There is no scalar. There is no loop. There are only array operations applied uniformly across entire structures. This is tacit programming. You describe the transformation, not the iteration. When you write a rank 2 matrix multiply in APL, you are not telling the computer to loop over rows and columns. You are declaring a structural transformation between two arrays. Fortran treats the array as a convenience. APL treats the scalar as a special case of an array of rank 0. These are opposite philosophies, and they produce opposite languages. Now here is the industrial punchline. APL's direct descendants, JK and Q, are the dominant computation languages in high-frequency trading and quantitative finance today. KDB+, which runs on Q, processes billions of time series records per second at firms like Goldman Sachs and Citadel. Why? Because APL's array first model maps directly onto how financial data actually exists, as time-indexed vectors and matrices, not as individual records. And NumPy's broadcasting rules, which confuse every Python beginner, are APL semantics with Python syntax bolted on top. Understanding APL explains NumPy. That connection changes how you teach and how you debug. Next, we move from arrays to types, and into perhaps the most intellectually powerful archetype of all. The third member of Group A is ML. And I want to be very precise about what ML contributed, because it is frequently misunderstood, even by experienced engineers. And developed at Edinburgh in the 1970s by Robin Milner, did not just add types to a language. It invented a completely different relationship between the programmer and the type system. In every language before ML, types were runtime guardrails. You declared types to help the compiler catch errors that would otherwise crash at runtime. ML inverted this. In ML, the type system is a proof assistant. When your ML program type checks, you have proven that certain classes of errors are impossible, not improbable, impossible. The mechanism is Hindley-Milner type inference, which allows the compiler to deduce the most general type of every expression without any annotations from the programmer. This is a formal logic result, not a heuristic. Now trace the descendants. Haskell took ML's type system and pushed it to its logical extreme with type classes and monadic I/O. OCaml added a practical module system for large-scale programming. FSharp brought ML semantics onto the .NET runtime, and Rust, and this is the insight that changes how you understand Rust. Rust's ownership and borrow checker is an ML family type system extended with a linear type discipline to reason about memory lifetimes at compile time. Rust is not a systems language that happens to have types. Rust is an ML family language that happens to compile to bare metal. For the PE exam, recognize this. Hindley-Milner is the theoretical foundation behind every modern type inference system, from TypeScript's structural inference to Kotlin's smartcasts. The entire modern shift toward safer, more expressive type systems traces back to this one archetype. In the next section, we leave the world of transformation and enter the world of process, where computation is not what you calculate, but what you do. We now enter Group B, computation as process. And this is the archetype that most working developers live inside every single day without recognizing it. Algol, developed by an international committee in 1958 and refined through Algol 60 and Algol 68, established a thesis that now seems obvious because it won so completely. Mutation is a structured sequence of state mutations organized within nested scopes. Let me unpack what that means architecturally. Algol gave us block structure, the idea that a program is a hierarchy of nested blocks, each with its own local variables that are invisible to the outside. This is lexical scoping. Before Algol, scoping was dynamic, ad hoc, or non-existent. Algol made lexical scope the default, and every mainstream language since has followed. Algol also established recursion as a first-class feature, not an afterthought. And critically, Algol separated the specification of an algorithm, its logical structure, from its physical machine representation. This is the Bacchus form origin. Algol was the first language defined by a formal grammar, making language specification itself a CS discipline. Now look at the descent. C is Algol with manual memory management. Pascal is Algol with stricter type discipline. Java Algol with objects and garbage collection. Go is algol with Go routines and a deliberately minimalist feature set. When Go's designers say they wanted a simple language, what they mean is we want pure algol process semantics without the accretion of 4 decades of additions. Understanding algol tells you exactly Go feels the way it does. But algol had one blind spot, and a researcher in Norway in 1967 identified it and added the one feature that changed everything. That story comes next. In 1967, Ole Johan Dahl and Kristen Nygaard at the Norwegian Computing Center published Simulus 67, and the single addition they made to algol's process model is the source of the entire object-oriented programming lineage. Every class you've ever written traces back to this one decision. Here is the insight. Algol processes have behavior but no persistent identity. A procedure runs, transforms state, and disappears. Dahl and Nygaard asked, what if a process could remember its own state between invocations? What if it had identity, a persistent existence in memory, with its own private data? That question produced the class. An object in Simula is an algol process that persists. It has its own activation record that does not get destroyed when control returns, what we now call instant state. And crucially, objects communicate by sending each other messages, not by sharing global state. This is Simula's design thesis. Computation is a community of persistent, identity-bearing processes exchanging messages. Now trace the lineage. Bjarne Stroustrup studied Simula before designing C++. He explicitly called C++ SUL with Simula classes. James Gosling designed Java with Simula's class hierarchy as the central organizing principle. Every Android app written in Kotlin, every iOS feature written in Swift, they are all expressing Simula's identity-first model. The entire enterprise software industry, SAP, Oracle ERP, framework, is built on Simula's architectural bet. But here is the tension that this archetype creates, and it is a live debate in language design today. The tension between algol's process-first world and Simula's identity-first world is exactly the argument happening between Go developers and Java developers right now. Now let us make the tension explicit, because this is one of the most practically useful insights in this entire lecture series. Algol and Simula are both in your codebase right now, fighting each other. Algol's model says, computation is a procedure applied to values. Values do not have identity. 2 integers with the same value are the same thing. State mutation is explicit and local. Procedures are transformations when possible. This is Go's philosophy. Go has structs, not objects. It has functions, not methods with virtual dispatch. When Go developers say prefer composition over inheritance, they are reverting from Simula back toward algol. Simula's model says, computation is a conversation between entities. Entities have identity. 2 objects with the same field values are still different objects because they exist at different memory addresses. This is Java's philosophy. Java's equals versus double equals problem. The entire identity versus equality debate in every OP language is Simula's persistent identity assumption colliding with algol's value semantics. When a Java developer and a Go developer argue about whether to use interfaces or inheritance, they aren't arguing about syntax preferences. They are arguing about which archetype is correct. For the PE exam and for real system design, the answer is neither is universally correct. They optimize for different problem domains. Simula's model excels when entities have genuinely persistent, evolving identities, financial accounts, user sessions, simulation actors. Algol's model excels when computation is fundamentally stateless transformation, request handlers, data pipelines, concurrent services. The language you choose is a statement about which model fits your domain. In the next section, we meet the 2 most philosophically opposite archetypes in the entire classification, and they will permanently change how you think about language design trade-offs. We arrive at the most philosophically provocative archetype in the entire classification. Lisp, designed by John McCarthy at MIT in 1958, makes a claim that sounds like a paradox until you understand it. There is no meaningful distinction between code and data. A Lisp program is a list. The data your Lisp program processes is also a list. The macro that transforms your program before it runs, the Lisp program operating on a list that happens to be code. This property, that the language's code is written in the language's own data structure, is called homoiconicity, and it is the most powerful metaprogramming foundation. Here is why this matters practically. In every other language, if you want to extend the language itself, to add a new control flow construct, to build a domain-specific language, to implement lazy evaluation, you need to modify the compiler or use brittle text-based macros. In Lisp, you write a function that takes code as input and returns new code as output. Your macro is a first-class citizen, indistinguishable from a regular function. This is how Clojure implements its concurrency primitives. not as language-level keywords, but as Lisp macros that transform code at compile time. This is how Racket becomes a language laboratory. The entire Racket ecosystem of teaching languages, type-checked variants, and domain languages is built on Lisp's homoiconic foundation. And Elixir's macro system, which enables the Phoenix framework's declarative routing and live views reactive templates, is directly descended from Lisp's metaprogramming model. Even Rust's procedural macros, which look nothing like Lisp, are implementing Lisp's core idea. Code transformation is just data transformation. But Lisp's maximum flexibility model comes with a cost, and that cost is exactly what COBOL was designed to eliminate. Now, I want to do something that most CS curricula refuse to do. I am going to defend COBOL as a serious, coherent design archetype with a distinct philosophy that solved a real problem better than any of its contemporaries. COBOL, standardized in 1960 under Grace Hopper's influence and the Codicil Committee, makes this claim. Computation is the transformation of named business records, and the person who specifies what to compute should be able to read the program that computes it. This is a radical user experience position embedded at the language level. COBOL's syntax reads like English business prose intentionally, not because Hopper did not know how to write a concise language, but because the specification requirement was that a non-programmer business analyst should be able to audit a COBOL program and verify that it correctly implements a business rule. This is the first ever attempt to make programs legible to domain experts, not just to programmers. The design consequences are profound. COBOL gave us the named field model. Data items have hierarchical names, not just memory addresses. A COBOL record structure with its level 88 condition names is the direct ancestor of SQL's named column model and JSON's named property model. The human-readable constraint led directly to declarative specifications. SQL's select clause reads like COBOL's move statement extended to set operations. SAP ABAP, which runs the financial systems of most Fortune 500 companies, is a direct COBOL descendant with an object layer added. The U.S. Federal Reserve, most global banking core systems, and an estimated 800 billion lines of COBOL in production today are not technical debt. They are a validation that COBOL's design thesis was correct for its domain. The surprise insight. When you design a DSL for business users today, you are making COBOL's same design bet. Now we bring Lisp and COBOL in direct confrontation, because this comparison is the most useful analytical frame for anyone designing a DSL, building an internal tooling language, or choosing how to extend an existing system. Lisp and COBOL are both correct answers. They are correct answers to fundamentally different questions about who the primary user of the language is. Lisp asks, how do we give expressive power to a programmer who needs to solve problems we cannot anticipate? The answer is homoiconicity and macros. Give the programmer the ability to reshape the language itself. Flexibility is the supreme virtue. COBOL asks, how do we make a program legible and audible by the business stakeholder who owns the requirements? The answer is named records and English-like syntax. Make the program itself the specification document. Legibility is the supreme virtue. When you face a DSL design decision today, you are choosing between these poles. If your users are other developers who need expressiveness, Lisp's model. Build a macro system. Embrace composability, accept that the learning curve is steep. If your users are domain experts who must be able to read and audit the programs, COBOL's model. Build a constrained verbose, readable syntax. Accept reduced expressiveness in exchange for auditability. Kubernetes YAML configuration is COBOL philosophy. Terraform HCL is COBOL philosophy. Configuration is an unfortunate attempt to be Lisp philosophy with JavaScript. SQL is the synthesis that took COBOL's named record model and added just enough declarative composability from the relational algebra tradition. This is not ancient history. Every infrastructure as code framework, every workflow DSL, every business rules engine you design in the next decade force you to choose between Lisp's flexibility and COBOL's legibility. Know which choice you are making. And now that we have profiled all 7 archetypes and their design DNA, the next chapter does something even more powerful. It builds the complete genealogy map, tracing every major modern language you use today back through the exact branching path of influences and design decisions that produced it. The map will you. Before we map a single language, we need to establish the rules of the genealogy tree. Because without rules, a map is just noise. Every modern programming language has exactly one dominant archetype lineage. That dominant lineage is not merely a historical curiosity. It is the DNA that determines the language's core trade-off profile, how it handles types, memory, and execution model. Think of it like blood type. You may have influences from multiple ancestors, but Your dominant governs how your immune system, or in our case, your runtime, actually behaves. Secondary influences exist. Absolutely. Rust borrows ML's type theory. Python borrows Lisp's dynamic evaluation. But here is the critical rule. The dominant archetype always wins when the two conflict. If you ignore that rule as a developer, you will spend your career fighting your own language. The genealogy map we are building today will show you exactly where each modern language sits, which root it grew from, and which secondary lines it grafted onto itself. Once you can read this map, you will never again wonder why a language behaves unexpectedly. The behavior was always predicted by the ancestry. In the next scene, we will see what happens when a language tries to inherit from two dominant archetypes simultaneously, and what that costs the developer. Multi-paradigm is one of the most celebrated terms in modern language marketing. Scala is multi-paradigm, Python is multi-paradigm, Kotlin is multi-paradigm. The marketing is correct, but it omits the hidden cost. When a language inherits from two archetypes, it does not give you the best of both worlds for free. It gives you the obligation to understand both worlds simultaneously. Consider Python. It inherits Algol's block-structured imperative model and Lisp's dynamic evaluation model. If you write Python purely in the Algol style, procedural mutable state, explicit loops, you pay no cost for the Lisp ancestry. But the moment you use decorators, metaclasses, or runtime attribute injection, you are activating the Lisp lineage. And if you do not understand the Lisp model, you will write code that behaves in ways that feel like bugs, but are actually features of an ancestor you never studied. Scala makes this even more extreme. Its ML type system ancestry and its Simula object-oriented ancestry produce genuine design tension in the language itself, not just in how developers use it. The compiler itself had to make compromises that neither pure ML nor pure Simula would have accepted. The lesson here is architectural. Every secondary archetype is not a free feature. It is a deadline that accrues interest when a developer encounters the conflict. The question is not, does my language support functional programming? The question is, do I understand which ancestor is speaking when this code behaves unexpectedly? Stay with me. Because next we are going to see the complete map of all 10 modern languages laid against all 7 roots. Now we see the complete picture. This is the genealogy diagram, 7 roots, 10 modern languages, and every inheritance line mapped explicitly. At the Algol root, we find Go as its purest descendant, and Rust as a hybrid pulling strongly from both Algol and ML. At the Lisp root, we find Clojure as its modern expression, and Python drawing a secondary line from Lisp's dynamic evaluation. At the ML root, Haskell stands as the most extreme pure expression, while Rust grafts ML's type theory onto Algol's process model. At the Simula root, Kotlin sits as a refined Simula-Algol hybrid, the JVM's answer to clean object-oriented design. Scala also claims the Simula root, but reaches further into ML territory than any other mainstream language. TypeScript inherits from the Algol-Simula intersection through JavaScript's lineage, adding L-style structural typing as a secondary influence. Swift draws from both Simula's object model and ML's type safety, targeting the domain of systems UI programming. Julia is a fascinating case. It roots primarily in the APL Fortran scientific computing tradition, with Lisp-style metaprogramming as a secondary influence. And Elixir sits at the Erlang-Actor model root, which we trace back to Simula's identity-based concurrency vision, extended with Lisp's macro-expressiveness. The map is now complete. Every language you will encounter in your career lives somewhere on this tree. And in the next section, we are going to take 5 of these languages and ask a deeper question. Not just where they sit, but why their specific position explains every frustrating or delightful behavior you have ever experienced with them. Let us begin the case studies with Rust, the language that has topped the Stack Overflow Developer Satisfaction Survey for 8 consecutive years, and yet carries the steepest learning curve of any systems language introduced in the last 2 decades. That paradox is explained entirely by its ancestry. Rust is not, as its marketing sometimes suggests, a safer C. It is something far more precise. It is an ML-style proof assistant philosophy applied on top of an Algol process execution model. Look at the stack. At the bottom, you have Algol's control flow primitives, deterministic sequential execution, structured blocks, explicit resource lifecycle. This is Rust's performance comes from. It inherits Algol's direct correspondence between source code and machine instruction. On top of that, Rust places ML's type system, specifically a variant known as affine types, sometimes called linear types. In ML's proof assistant tradition, a type is not merely a tag on a value. A type is a proof that a program property holds. When the Rust compiler tells you that you cannot move a value that has already been moved, it is not enforcing an arbitrary rule. It is completing a proof that no 2 owners can simultaneously modify a memory location. The borrow checker is ML's type inference engine, retargeted from proving mathematical theorems to proving memory safety theorems. This is why Rust's learning curve feels like it requires a PhD, because in a very real sense, you are learning to write proofs, not just programs. The algol layer handles how the machine executes. The ML layer handles prove that execution is safe before it runs. Understanding that Rust is a two-layer system, not a single language, is the single most important insight for anyone trying to teach or learn it. But here is the uncomfortable question. If Rust is essentially ML applied to systems programming, why did we not just use ML for systems programming? The answer reveals a fundamental tension in language design, and we will see a mirror of that tension when we look at Go next. Now consider the opposite design decision. If Rust said yes to ML's complexity in exchange for its safety guarantees, Go said no, deliberately, loudly, and repeatedly. Go is the most consciously pure algol descendant in modern use, and understanding that purity explains every Go design choice that frustrates developers coming from other lineages. Go's designers, Ken Thompson, Rob Pike, Robert Griesmer, had a specific enemy in mind: complexity that accumulates silently over time in large codebases. Their diagnosis was that both Simula's object identity model and ML's type system complexity were primary contributors to that accumulation. So they removed both. Go has no inheritance hierarchy in the Simula sense. No is a relationships defined at the class level. Go's interfaces are structural, not nominal, which is actually Clogel's duck-type procedural world than to Simula's closed-class taxonomy. For the first 10 years of Go's existence, it had no generics. This was not an oversight, it was a statement. ML's parametric polymorphism makes type reasoning more powerful, but also more complex. Go's designers believed that the complexity cost exceeded the expressiveness benefit for their target domain. Large-scale distributed server software built by large teams. Here is the insight that developers from Scala or Haskell backgrounds consistently miss. Go developers do not celebrate constraints despite being inconvenient. They celebrate constraints because inconvenience at the language level prevents a specific class of architectural mistakes at the system level. The explicit handling, the flat package structure, the absence of operator overloading, every one of these is algol's readability-first philosophy operationalized as language policy. Go is not a failed attempt at being Rust or Haskell. It is a successful attempt at being the most legible algol descendant possible. And the numbers of production systems running Go at Google, Cloudflare, and Docker prove that this was a valid engineering bet. But Go's purity also means it has a ceiling, and the languages that try to transcend that ceiling pay a very specific price. Python is the world's most popular programming language by most current measures, and it is also the most misunderstood from a design ancestry perspective. Most developers think of Python as easy algol. It has blocks, it has loops, it has functions, it feels sequential and imperative. But Python is not algol, with nicer syntax. Python is a deliberate three-way hybrid, and each of its three ancestors contributed something that the other two could not. From algol, Python's block structure and imperative sequencing. Your for loops, your if statements, your function definitions, that is, algol's gift. From Lisp, Python takes dynamic evaluation, the ability to treat code as data at runtime. Decorators are Lisp macros in disguise. Metaclasses are Lisp's def macro system applied to class construction. The eval function is literally Lisp's eval. When Python introspects an object at runtime, modifies a class after definition, or generates code dynamically, it is exercising its Lisp ancestry. And from COBOL, this is the ancestor most Python developers have never considered. Python takes its readability-first philosophy. COBOL was designed to be readable by non-programmers, by business stakeholders. Python's insistence that there should be one obvious way to do it, its preference for explicit over implicit, its English-like keyword choices, these are COBOL's influence on what a programming language should communicate. Now look at where Python feels inconsistent. Its type discipline has always been contested, because algol wants types to be structural contracts, and Lisp wants types to be runtime discoverable tags. Python's type hint system, introduced in Python 3.5, is algol influence trying to reassert itself against Lisp's dynamism. The fact that type hints are optional and unenforced by the runtime is the Lisp ancestor refusing to be fully overridden. Python's inconsistency is not a design failure. It is the predictable output of three ancestors who do not fully agree. And the most fascinating case of ancestral disagreement in modern languages is the one we examine next, where two languages both claim to be functional, but have completely incompatible answers to what a program even is. Both Haskell and Clojure will tell you they are functional languages. Both communities will insist that functional programming is the right way to model computation. And yet, if you sit a Haskell developer and a Clojure developer in the same room and ask them what is a program, you will get two answers that are not merely different, they are architecturally incompatible. Haskell is ML taken to its logical extreme. In ML's ancestry, a program is a mathematical proof expressed in code. Functions are total, they must handle every possible input. Side effects are quarantined into a type-level construct called the I/O monad, because in Haskell's world, a function that reads from disk is not a function. It is a proof that has been weakened by interaction with the physical world. Haskell's type system can express propositions that no runtime check could ever verify. The compiler is the proof assistant. If the code compiles, the proof is valid. This is ML's philosophy at maximum intensity. Clojure, by contrast, is Lisp's modern expression. And in Lisp's ancestry, a program is a transformation applied to a running system. Lisp was built for repeal-driven development. You modify the program while it is running. Clojure inherits this. Its repeal is not a development convenience. It is the primary interface to the computation model. Where Haskell quarantines effects into types, Clojure manages effects through persistent immutable data structures and software transactional memory, runtime mechanisms, not compile-time proofs. When Haskell says prove to the compiler that this is safe, Clojure says design your data so that concurrent modification is harmless by construction. Safe concurrent computation, radically different answers rooted in different ancestors. This distinction matters enormously for system architecture decisions. Choosing Haskell means choosing compile time correctness guarantees. Choosing Clojure means choosing runtime flexibility and repeat-driven system evolution. Neither is universally superior, but each answer was determined by an ancestor that was designed in a different decade for a different world. And in our final section, we are going to confront the most dangerous pattern in language selection: choosing a language for its secondary features and ignoring what its dominant ancestor will demand from your entire team. Scala is the most instructive cautionary tale in modern language design, not because it failed as a language, because it succeeded too completely as a hybrid, and that success became its own obstacle. Scala set out to unify ML's type theory with Simula's object-oriented model on the JVM. The ambition was genuine and the execution was technically brilliant. Scala's type system is arguably the most powerful of any mainstream language. It can express higher-kinded types, path-dependent types, and type class hierarchies that make Haskell developers pause in admiration. Its object model is also elegant. Everything is an object, functions are objects, and the class hierarchy is clean. But here is the architectural problem. ML's type theory and Simula's identity model are not just different. They have different answers to the question of what identity means. In ML, identity is structural. Two values are equivalent if they have the same type and the same content. In Simula, identity is referential. Two objects are equivalent only if they are the literally same object in memory. Scala has to accommodate both answers simultaneously. And the result is a language where the correct approach to any given problem depends heavily on which ancestor's model you are currently operating in. Implicits, type classes, variance annotations, path-dependent types. Each of these is a mechanism that exists to mediate the conflict between the two ancestors. The engineering velocity cost became visible at scale. Companies like Twitter and LinkedIn, early adopters, eventually restricted the subset of Scala features their teams were permitted to use, effectively enforcing a single ancestor discipline on a dual ancestor language. Kotlin is the corrective response. It took Simula's object model, accepted ML's type safety as a secondary discipline, and deliberately refused to go as deep into ML territory as Scala did. TypeScript made the same corrective bet. Structural ML-style typing as a secondary layer on top of JavaScript's Algol Simula base, with an explicit escape hatch back to dynamic Lisp-style behavior via the any type. The pattern is consistent. Maximum hybridization produces maximum expressiveness and maximum conceptual surface area. Engineering organizations consistently trade the former for relief from the latter. Now, given everything you have seen about ancestry, how do you actually use this framework to make a language selection decision? We have now traced 7 roots, 10 modern languages, 5 detailed case studies, and 1 major cautionary tale. The question that remains is the only question that matters in practice. How do you use this framework to make an actual language selection decision? The answer is a decision heuristic in 3 steps, and it is the most reliable tools I have seen applied in enterprise architecture reviews over the past 2 decades. Step 1. Model your problem domain first. Before you look at any language, ask, what is the dominant model of my problem? Is it data transformation with correctness guarantees? That is the ML domain. Is it long-running stateful objects that send messages to each other? That is the simulactor domain. Is it sequential data processing where readability matters more than type safety? That is the COBOL-ALGOL domain. Step 2. Match your dominant archetype. Choose a language whose dominant ancestry aligns with your problem's dominant model. Do not choose a language for its secondary features. Secondary features are what you learn after the team has mastered the dominant model. Step 3. Budget explicitly for every secondary archetype. If your chosen language has secondary ancestry, calculate the train investment required for your team to understand that Ancestor's model well enough not to fight it. This is not optional. Organizations that skip this step produce code bases where half the team writes in one ancestral style and the other half writes in another. And code review becomes a negotiation between two incompatible worldviews instead of an engineering quality gate. The genealogy map you have seen in this chapter is not academic history. It is an architectural risk assessment tool. Every node on that map, what your team must understand before they can use that language without fighting its own design. In the next chapter, we go deeper into the design principles that separate these 7 ancestors, specifically how each archetype made fundamentally different choices about type systems, memory models, and concurrency. Those 3 dimensions are the axes on which every language selection decision should be made. And knowing the ancestry tells you exactly where which language is on all 3 axes before you write a single line of code. Every debate you have ever had about static versus dynamic being, every team argument about annotations, every code review disagreement about type hints, is actually an archetype debate in disguise. Let me show you why. Each of the 7 ancestor languages answers the question, what is a type, in a fundamentally different way, and those answers have never converged. ML treats a type as a mathematical proof. If your program type checks, you have formally proven a class of errors cannot exist. This is the Curry-Howard correspondence in practice. ALGOL treats a type as a compiler hint, a contract between programmer and machine that enables optimization and early error detection, but nothing deeper. Lisp treats a type as a runtime assertion. Types are properties of values, not variables, and you check them when you need to. COBOL treats a type almost as documentation. PEX 9.5 is a human-readable specification of business data shape, not a formal constraint. Assembly and Fortran treat types as storage layout directives, telling the hardware how many bytes to reserve. These are not different points on a single spectrum. They are genuinely different philosophical stances on what software correctness means. And this is exactly why type debates feel so unresolvable. That the participants are often operating from different archetype axioms without realizing it. But here is the provocative question. What happens when you try to mix these philosophies inside a single modern language? Now let us confront the uncomfortable truth about gradual typing. The feature that TypeScript, Python type hints, and TypeDracket all represent. Gradual typing is an attempt to retrofit ML family type philosophy onto a Lisp family or ALGOL family foundation. And the result, as you have probably felt in practice, always carries a faint smell of incompleteness. Here is why. When Python was designed, Guido van Rossum made a deliberate Lisp lineage choice. Types belong to values, not to names. The variable x does not have a type, the object that x currently points to does. That is a deep architectural commitment, not a surface choice. When you add type hints with PEP 484, you are layering an ML family annotation system on top of that Lisp family runtime. The type checker, MyP or PyWrite, runs as a separate pass that simply does not exist in the Python runtime. The types are erased at execution. Contrast this with Haskell. Types are not annotations, they are the program. The distinction is not cosmetic. In TypeScript, you can always use any and escape the type system entirely, because the underlying JavaScript runtime has no concept of type-level proofs. This escape hatch is not a design flaw. It is an honest acknowledgement that you are running 2 archetype philosophies in parallel, and they do not fully merge. The lesson for practitioners: when you evaluate a gradual type system, always ask which archetype the runtime belongs to. The answer tells you exactly where the type system will fail you. And that insight sets up a deeper question about memory, which we address right now. Here is a claim that will reframe how you think about Rust, Go, and Java all at once. Memory management is not a feature that language designers freely choose. It is a direct consequence of the archetype. It flows necessarily from the type and execution model the archetype already commits to. Let me prove this with 3 archetypes. Fortran's archetype assumes static, predictable computation. You know at compile time what data you need, how large it is, and how long it lives. Static allocation is not a limitation, it is the correct answer for that execution model. COBOL inherits the same instinct. ALGOL's archetype introduces the procedure abstraction and lex scoping, and that single choice makes stack discipline mandatory. Procedures locals must lie as the procedure's activation. The stack frame is not a performance trick, it is the memory semantics of ALGOL's core abstraction. Now consider Lisp. Lisp's archetype is the lambda, anonymous functions creating closures over environments, data structures of arbitrary and unpredictable shape, programs that generate and manipulate other programs. You cannot know at compile time when a closure's environment dies. You cannot use a stack. Garbage collection is not a convenience feature added to Lisp. It is the only memory model that does not violate Lisp's fundamental abstraction. And ML can often statically prove ownership through its type system, which is exactly what Rust formalizes into an ownership and borrow checker. Rust did not invent a new idea. It took ML lineage type theory and made memory management a theorem you prove at compile time. The architecture was always there. So before you argue about GC versus manual memory, ask archetype you are actually inside. The answer is already decided. Now let us make this concrete with a table that every engineering team should have on the wall when choosing a runtime for a new system. The memory safety versus latency trade-off is not random. It maps directly onto the archetype spectrum. At one end, Rust's ownership model, ML lineage type theory applied to memory. Memory safety as a compile time proof. Zero garbage collect pauses. The cost, borrow checker learning curve, longer development time on first pass, explicit lifetime annotations for complex data structures. This is the choice for systems where latency variance is existential. Embedded firmware, real-time trading engines, operating system kernels. In the middle, Go and Java, ALGOL, and Simula lineage respectively. GC with tunable pause times. Go's concurrent GC typically delivers sub-millisecond pauses in well-tuned systems. Java's G1 and ZGC push toward microsecond territory. The cost, you will still occasionally see GCC jitter in production under memory pressure, and the JVM's warm-up behavior makes cold start latency unpredictable. This is the correct trade-off for microservices and application servers, where developer throughput matters more than microsecond latency. At the other end, Python, Ruby, Lisp descendants. GC is unavoidable and the language gives you minimal control over it. The trade-off is explicit. You are buying development speed and expressiveness and paying with runtime predictability. There is no universally correct answer here. There is only the answer that matches your archetype and your production constraints. And here is the critical insight for senior engineers. When your team debates should we rewrite this in Rust, they are actually asking whether they want to change archetypes. That is a much bigger decision than it sounds. Ready to see how concurrency makes the same argument? Concurrency is where the archetype differences become most visibly painful in production systems. And the reason is the same pattern we have seen twice already. Each archetype has a natural concurrency model that flows from its core abstractions, and when you try to use a different model, you are fighting the archetype. Simula's defining abstraction is the object, an entity with encapsulated state that sends messages to other entities. But in practice, Simula lineage languages like C++, Java, and C# defaulted to shared mutable state with base synchronization. Why? Because the object state was made directly accessible in memory, and threads are just objects running simultaneously. The result, data races, deadlocks, and the entire concurrent programming hell that dominated the 2000s. This was not inevitable, it was an archetype choice made under hardware constraints. Now contrast with Lisp lineage languages. Erlang traces to a functional Lisp-influenced design philosophy, introduced the actor model. Every process has strictly isolated state. Communication happens only through message passing, and a process crash cannot corrupt another process state. Elixir inherits this directly. There are no shared mutexes because there is no shared memory. The concurrency model follows naturally from the functional isolation that Lisp's lambda calculus demands. ML lineage takes a different path. Software transactional memory, or STM, treats concurrent state access as database transactions, optimistically execute, detect conflicts, roll back, and retry. Haskell's STM is the canonical example. It works because ML's type system can enforce that transactional blocks contain no side effects. And then there is Go, ALGO lineage, with Tony Hoare's CSP, formalized into Go routines and channels. The motto "do not communicate by sharing memory. Share memory by communicating" is not a Go invention, it is ALGO lineage meeting CSP theory. Each model, correct, inside its archetype. The failures happen at the boundaries. Can you guess where async await sits in this map? And now the timeline that pulls everything together. Async await. This syntax is now present in JavaScript, Python, C#, Rust, Kotlin, and Swift simultaneously. It looks like a universal consensus. But it is not. It is a surface syntax agreement over fundamentally incompatible underlying models, and tracing those models back to archetypes explains exactly why async code behaves so differently across languages. The history begins not with JavaScript in 2015, but with cooperative multitasking concepts from the 1960s and green thread models from ML lineage research systems in the 1980s and 1990s. C# introduced async await to the mainstream in 2012. Algol lineage, built on top of the task parallel library, which is a thread pool abstraction over the CLR's managed thread model. Python adopted the syntax in 2015 with PEP 492s. But Python loop is a single-threaded cooperative scheduler inherited from the Lisp lineage everything is an object that can be inspected at runtime philosophy. Rust's async await, stabilized in 2019, is fundamentally different from both. It generates state machines at compile time with zero runtime cost, and the ownership model guarantees that no async task can create a data race. The type system proves it. JavaScript's async await wraps an event loop model, closest to a Lisp lineage cooperative scheduler, but the syntax makes it look like C# continuation passing. This is the archetype illusion at maximum visibility. The same keyword, completely different execution guarantees, completely different failure modes. And this is precisely what Chapter 6 will equip you to diagnose in your own codebase. The self-diagnosis framework that lets you identify which archetype you are actually operating inside, and which archetype decisions are causing your team's most persistent production problems. That chapter is where the theory becomes a tool you use every day. Let's run the self-diagnosis right now. Theory, just 3 invariant questions. Question 1. Does your language treat memory as a value you own, a reference you borrow, or a region the runtime manages? Question 2. Does the type system enforce correctness at compile time, at runtime, or does it largely step aside? Question 3. Is concurrency modeled as shared mutable state, message passing actors, or deterministic data flow? Answer those 3 questions about Python, managed memory, dynamic runtime types, GIL-constrained shared state, and the flowchart points directly to the Lisp archetype branch with a secondary pull from Algol's structured control flow. Answer the same questions about Rust, owned memory with borrow checker, static algebraic types, fearless concurrency via ownership, and the pointer lands squarely on the ML archetype. The critical insight here is the flowchart is not asking what syntax your language uses. It is asking which philosophical commitments your language made when it had to choose. Every language had to choose. None escaped. And once you see where your language sits on this map, you will understand in seconds why switching from Python to Haskell feels like learning to walk again, while switching from Rust to Swift feels surprisingly familiar. But knowing your own archetype is only half the story. The real danger is what happens when you don't know the distance to your next language. Here is a bias that affects almost every experienced developer, and almost no one talks about it explicitly. When you have spent 3 or more years in single archetype, your mental model of what a programming language is gets silently calibrated to that archetype's invariance. A developer fluent in Python, a Lisp lineage language, intuitively expects late binding, duck typing, and a cooperative runtime. When they pick up Rust, they are not just learning new syntax. They are being asked to adopt the ML archetype's core belief that the compiler, not the runtime, is the authority. That shift is a paradigm replacement, not a vocabulary addition. Research in cognitive load theory, and frankly 25 years of watching developers onboard onto new languages in enterprise teams, consistently shows that adjacent archetype transitions, say Java to Kotlin, both Algol, ML hybrids, take weeks. Non-adjacent transitions, say JavaScript to Haskell, from Algol Lisp hybrid to pure ML, take months, and often stall permanently not because the developer lacks intelligence, but because the archetype distance is never named or measured. The genealogy map gives you that measurement. Before you assign a next language to yourself or to a team member, locate both languages on the map. If they share no archetype ancestor within 2 generations, budget for a 6-month ramp, not a 6-week sprint. In the final section, we will crystallize everything into a table you can carry into any architecture review or any exam room. Let us consolidate everything into the structured table every engineer should be able to reproduce on demand, whether in an architecture review, a technical interview, or a response. 7 archetypes. 7 core theses. Each one answered a different version of the question, what is a program, fundamentally? Fortran said a program is a numerical computation mapped to hardware. Algol said a program is a structured sequence of logical steps with scoped control flow. Lisp said a program is data that can examine and transform itself. COBOL said a program is a business process description readable by non-programmers. APL said a program is a mathematical notion applied uniformly to arrays. ML said a program is a proof, a typed expression that cannot be ill-formed if it compiles. And Simula said a program is a simulation of interacting real-world objects. Your modern language you use is a weighted combination of these 7 answers. Python weights Lisp heavily, adds algol structure, and borrows Simula's object model. Rust weights ML's type theoretic proof discipline, borrows algol's structured control, and discards Lisp's runtime entirely. Go weights Simula's actor-like concurrency, borrows algol's imperative structure, and deliberately minimizes ML's type complexity. When you can state that sentence for your own language, and defend why those weights were chosen, you have moved from language user to language architect. That is the vocabulary the 정보관리기술사 exam expects. That is the vocabulary a principal engineer uses when writing language selection criteria into an ADR. But there is one more reframe that changes how you read every language war thread you will ever encounter, and we will deliver it in the final 60 seconds. The Rust versus Go versus Python debate consumes enormous energy in engineering communities every year. Teams argue about performance benchmarks, ecosystem maturity, hiring pool size, syntax preference. All of those are real considerations. But notice what is almost never said in those debates. These 3 languages are not competing to solve the same problem from different angles. They are expressing 3 fundamentally different answers to the question of what a program is. Python, weighted toward Lisp, believes the runtime is a collaborative partner that can make reasonable decisions on your behalf. Go, weighted toward algol and Simula, believes that simplicity of model is more valuable than expressiveness of type. Concurrency should be a first-class citizen, not an afterthought. Rust, weighted toward ML, believes that if something can go wrong at runtime, it should be made impossible at compile time. These are not performance trade-offs. These are philosophical commitments with a 60-year lineage. Once you internalize this reframe, writing an architecture decision record changes entirely. Instead of writing "we chose Go because it is fast and has good tooling," you write, "We chose Go because our currency model aligns with the Simula algol archetype, CSP style message, passing with explicit GUID ownership boundaries, and our team's cognitive model is closest to the algol lineage." That sentence is defensible in a principal engineer review. That sentence survives the next language hype cycle. In the next lecture series, we will take this genealogy map and apply it directly to real-world architecture decision records, examining how companies like Google, Mozilla, JetBrains documented their language selection rationale, and what archetype logic was operating beneath every choice they made. The map is not the territory, but without the map, you are not navigating, you are just reacting. See you in the next series.